in an accumulating manner across that array. So in this case, the input array x is 0, 1, 2, 3, 4. So you're just adding each element to the sum as you go. So for example, multiply in this case gives you all zeros because x started at 0. So it's just multiplying 0 by 1 and then that by 2. So you get all zeros. On y, it doesn't start with 0, so it's a little bit more illustrative. Yeah. Yeah, so like those basically give you equivalent output. But sometimes, there might be some function that doesn't have a built-in NumPy function to do this, or not a built-in one, but a separate one.
I think Max is an example of that.
Yeah, I think I might. Wait, what is?
Cumulative maximum.
Yeah. Oh, cumulative maximum. Yeah, that's a good example. Yeah, let's try that. So actually, let's see what x is. So we should be able to do np dot max. Yes, it's max dot accumulate. No.
I think you want max, not max.
Do I want maximum?
Yeah.
All right, well, it does work, though. If you had a more interesting vector. Actually, we should I wonder if reverse this. There. So this is reversing the order of x. So it's 4, 3, 2, 1. So the cumulative maximum is always 4 in that case. All right. Yeah. So there's like identity attributes of these things. This is kind of interesting. There's an outer method where it will take the inputs and take the outer product of them. It's a little bit more. So honestly, this is kind of an interesting trivia thing. It's good to know about, but I don't personally use these very much day to day. But in some cases, they can come in handy. All right, so those are sort of the functions that operate array-wise. NumPy also has functions that will do aggregates. So for example, if we have this 2D array with elements from 0 to 9, there's a sum function that will obviously do the sum. There's an alternate way to spell some of these. So you can do, instead of doing np.sum, you can do array.sum and call the sum method on the array. It does the exact same thing. Oh, here we go. Yeah, is this good? Okay. Yeah, I was a little worried it would go off the screen, but I think this is great. All right, so similar to sum, there's can people see the screen okay?
Do people see the screen okay?
As good as possible.
Okay.
Yeah.
There are, but I can't.
Is there a magic button up there?
I don't have any buttons. Adjust the what? Sorry. Oh, yeah. We can do import anti-gravity, though. Yeah. For people that don't know. There's some other Easter eggs we'll maybe get to later. All right, so yeah, sum mean, min and max, obviously. So for stuff like min and max, for example, you could also use the reduce method on the add operator. No, wait. Ah, right. So I got my notebook messed up here. Okay, this is the equivalent of sum, element-wise. So if up here I took z and I did sum and said I want to sum along the first axis, so that would be going down this way. So it's 0 plus 5 and 1 plus 6. You would get this. This is exactly equivalent as calling reduce on the same array and specifying the same axis. A tricky thing here is that if you just call, actually, oh, that's x. There we go. If you just call reduce without any axis, it will assume the first axis, whereas sum, it will sum over the entire array, so they're not exactly equivalent. All right, so this is just what I was showing there. All right, and there's a whole bunch of other aggregate functions, but I think Daniela will talk more about that when she does statistical summaries of numerical summaries of data. You don't bother creating that mask array separately. You just directly index x where x is less than 0 and set that equal to 0. So you get the same thing there. I'm pretty sure it's not copying. I think it's exactly the same as just doing literal slice. Yeah, I mean, literal slice, meaning the colons, I think just create slice objects. So yeah, so the question was, I think, that in Python there's a slice object, and so do something like this. Actually, I pretty much never do this. So I don't know if it'll work. No. Oh no, I need a comma here maybe. Yeah. So this is equivalent to doing 0, 2. But you almost never need to know that.
It's actually really handy if you want to apply slice to a bunch of arrays. And there's a numpy s underscore.
Oh yeah, the s underscore. Okay.
Slice using exactly the same syntax. So it's easier to work with than the Python.
Okay. All right. So I take that back. Some cases it's useful.
Try s underscore, and then treat slice as sorry, numpy dot s underscore, and then make a slice as
Like this?
Slice as you would if you were actually.
Ah, okay.
And I think it's with brackets, and it's square brackets.
Like this?
Yeah. And now x for x is bracket. So you can make your slices the way you would, and it's actually really handy if you have a bunch of data.
All right. Cool. And it's 1 character shorter.
Is the advantage of this just that it's the same syntax, or is it?
So it functions exactly like the Python slice. It's just that the syntax is what you think of as a slice, not the
You can write colons. So you can do more complex stuff than just simple binary operations. You can do, if you want to say, let's see, so what is it actually doing? Set all the other elements in the array that aren't for some crazy reason. If you wanted to set all these other elements equal to 0, you could do this invert operation on the mask. So this is saying, take that same mask that I would normally create and just swap all the trues and falses. Yeah.
I've been very clumsily using functions like logical and logical or for a number of years. Can you really just use these?
Yeah, I think these are just aliases for those. Same way that like plus is an alias for add.
Okay, thank you.
But the one important thing to keep track of is that there's like some tricky precedence rules with these. They have very high precedence. So make sure when you're doing these sort of binary operations to put things in parentheses. So if I didn't have these parentheses here, it would try to do this first before these operations. So here I'm saying, give me all the elements where x is less than 0 or x is greater than 0, or greater than 3. So so it got this one, and this one, as we think.
I ran into the problem trying that, but it tells me I should use numpy.all or numpy.any. And so I never actually figured out how to write it, because it always gave me an error saying, please use numpy.all.
Yeah, so you might have been doing like this. So if you just put normal Python ands or ors in there, you will get some message like the truth value of an array with more than one element is ambiguous. Use any or all. So this is because the and or operations in Python are control flow operations, so they have to only be straight normal Booleans. They can only be one thing. So they're not overloadable this way. So that's why NumPy uses the these are the pipe and the ampersand are called bitwise operators. So they're basically, for binaries on arrays, for comparisons on arrays, use the bitwise operators. Oops, sorry. Ampersand and pipe.
Since you're going to a new topic, just one addition. I found that using the mask slicing with booleans or the fancy slicing with indices that are not copying, that is massively slower than using the actual quick slicing, which can be very important if you're dealing with big data sets.
Yeah, definitely. I mean, so part of that is that it has to create a copy, right? All right. So the other, besides all the fancy indexing you can do, another nice feature of NumPy is the fact that it does broadcasting. So if you want to add, say, 3 to every element of this array, it just works even though 3 is not an array itself, right? So what's going on under the hood is that it is taking your input array x, and you're saying add 3. OK, I know how to translate that into an array that matches the input array. So it kind of like broadcasts the 3 to match the size of the input array, and then does the element-wise addition. OK, so this works in higher dimensions. If you have so this is a 2D array x, and I'm going to add it to a 1D array y. So the shape of x is 4 by 3, and the shape of y is just 3. So the shape of y will be padded. So this works, right? I can add x plus y and get what I expect. So what's happening is the shape of y is padded on the left before it does the indexing. So it basically turns y into a 1 by 3 array, and then does that broadcasting same as before. So in this case, to visualize it, it's sort of like this line here, where we've got x, this 2D array, y is this 1D array. And it's first saying, all right, take y and broadcast, sort of like map this across all the rows of x, right? And then do the operation. So this also works if x is just a 1 by, so in this case, x is a 4 by 1 array, and x and y is the same thing. You'll get the same thing here. Because it will map both x and y until the shapes match. So this should work. So the general rules here are that if the two arrays different dimensions, first it will add ones, dimensions with size 1, to the smaller array. So in these cases, y is smaller, so it adds a 1 over here, basically. Then, if the shapes do not match, the shape that's a 1 will get translated to match the other one. And it goes both ways. So in our last example, they were mismatching in that y had a 1 here and x had a 1 here, but they were both mapped to match. And then if they don't, if there's some non-matching thing, so if like x was 4 by 2 and y was 1 by 3, it would throw an error because one of them has to be 1 if they don't match, basically. All right, so yeah, definitely.
So when I do this, I always put nuns in explicitly to show to my future self which order I meant this to work.
Yeah, I do that in code that's gotten complicated with broadcasting. And sometimes it's necessary to do that even.
Explicitly tell it how to broadcast by throwing it nuns.
Yeah, so you can do,
Can you put in the nuns? Can you implement?
yeah, so here I think it would be none 1. Okay.
You can do the X as well, right?
Well, x is already two-dimensional here, so I don't want to add anything to it. Oh, wait, sorry. This should be like this, actually. Yeah, sorry, I got that wrong. So none will add another axis to y. You can also do mp.new axis if you want to be less confusing and write longer code, I guess.
Like if you get arrays that have like multiple, more than 1 or 2 dimensions, you kind of have to do this or it's just too confusing.
Yeah.
You don't have to, but I mean, yeah, you have to be Python expert.
Yeah, it can get confusing, but for simple stuff, like most of the time I'm using it where I have like a 2D array and a 1D array, and it's pretty obvious that I just want to map the 1D array across 2. For like 3 and higher D arrays, then it's like, okay, what's going on?
Often that time people think it's clear, and then they ask someone else to look at their code, and they come back to it and realize it wasn't clear. So whenever in doubt, make it easy for your future self or your advisor.
Yeah.
So what I've been doing that I guess is easy but pretty slow, I guess, is if you down a new axis and then reshape it. That's how I've been doing it. If I try to just add them and it won't broadcast, like if it gets confused with broadcasting, because I want to broadcast across like the third dimension or something.
Yeah, you can also do like x dot or y dot reshape
Right.
1, 3. Or actually, you have to call this a tuple. So we didn't talk about this, but if it can, you can tell it to give you an array with a different shape if it's compatible with the current shape. So here y is just length 3, so it's able to translate this into a 1 by 3 array because it has the same number of elements.
A little bit. Well, yeah. If you just like repeat or you tile it and then you reshape that
Oh, okay.
to
Yeah,
the
that
other direction.
will be slower because I think tile actually creates a copy.
But you can do the new axis thing and that's faster.
Yeah. Yeah, but yeah, you don't want to get too fancy because there's this rule of thumb that you have to be twice as smart to. It's twice as hard to debug the code than to write it. So if you are as clever as possible when you're writing the code, you by definition cannot debug it. All right, so just to wrap up the NumPy stuff, I have a couple of mini exercises here. So we're just going to take like a 5-minute break that sort of like illustrate all the stuff I just talked about. So what the problem is that so assume you have you have endpoints, say 1,000 in 5 dimensions, and you're representing that by a array of shape 1,000 by 5. So each row corresponds to a point, right? So what we're going to do is first I want people to actually, sorry. The important thing I left out here is that to make it a little more complicated for people, some of the values are missing, and they're represented by NaNs. Okay, so there's 10% missing values scattered throughout this array randomly. So actually, just to show people sort of what this looks like, this is the first 50 elements, 50 rows of this array that we're dealing with. So you see some of the rows have no nans, some of them have one. You know, they're sort of scattered randomly throughout. So first, I just want to compute the number of rows with no missing values at all. So for this, we're going to use, just as a clue, we're going to use the any and all operations, which we sort of talked about in passing. Then, using masking operations, I want to clean the array of the NaNs. And then finally use some broadcasting to compute the whitened version of the array. So this is the array with the mean subtracted and divided by the standard deviation of the points. So if people have the notebook, this is kind of important for this, I guess. Go. I think you have less than 10 minutes, actually. Yes, you have 5 minutes. Go. Oh, it should be the same thing as up here, actually. Ah, damn, you're right. Yeah.
You just put it to the one part.
Fixed it. There's probably some option to randint to not replace.
I think you can put replace equals false, possibly. Oh no, that only works for choice.
Yeah, you need to use
Choice.
Yeah. That's good enough. I just wanted some missing.
question about step 2.
Yeah.
Do you actually want the array cleaned, or is it acceptable to jump from 1 to 3?
Oh, I mean, this is. Well, I want to do this on the cleaned array, because otherwise you're going to have a bunch of. It's going to be. If you don't do this, then in 3 you're going to get all nans.
No, there's a way to do it.
Oh, really?
Yeah.
Oh, okay. Maybe you can give us a shorter version. I've got to remind myself how to answer this.
About that function.
Oh. Damn, I forgot about that. Yeah. Yeah.
That's why I asked.
Hey. Okay, so yeah.
Do we have any power outlets here? I forgot to charge my laptop.
Oh yeah, we have some. Danielle, do you know where they are?
No, someone else connected them.
They're hanging on this wall, but not very helpful.
Yeah, we brought a lot of extension cords, but there's only like 3 outlets in the room itself, so. Or we brought a lot of power strips, rather. I think we might need some more extension cords to. Yeah. Throughout the day, people are just going to shift. Yeah, I've got an empty one right here. All right, so I'm going to go ahead and try to live code the solution for this, so we can finish up this section in order to get coffee at 10:30. All right, so the solution here, the first thing that we need to do is have some kind of thing that tells us what elements are nan, right? And if you, this is like sort of a thing about floating point numbers, is that you can't just say equals equals nan to figure out which things are nan. So if you do numpy.nan equals numpy.nan, you get false. So equals doesn't work for nans. There's a kind of good reason for that, but it's definitely like gotcha. But as with most things, there's a convenient numpy function called isNan, and that will return true. Okay, so I guess this wasn't in the clue, but you have to use this isNan function to get the nan elements. So if you just do isNan on x, you will get a huge array that's 5,000 or 1,000 by 5, right? But we actually want to know which rows have any nans at all, right? Because we want to, if any row has nan, we just want to get rid of that row entirely, because it represents a point that has some sort of missing data. So for this, we are going to start with this calling isNan, but then call numpy.any on this. So if you just do plain any, it will tell you true, because yes, some elements of x are nan. What we want is to do any along an axis, and I can never remember exactly which one's which, so I usually have to play with it. And all right, so it's not that one. We want the axis that gives you a length 1,000 array out. Okay, so this expression is now telling me the rows where any element is nan. Okay. So now the first question here was to count the number of rows with no missing values. So what you could do is you want the ones that, this is telling you the ones that have some missing values, so you could just invert this. Oops. Or alternatively, you could call all and invert this. That should give you the same thing. So I'm going to leave it like this.
You can also do np that is finite, right?
Most of the time that will work, but I think like if you have an inf in there, like the np.inf for infinity, then won't that return false?
It's not finite, right?
It's not finite, but I don't want to mask those necessarily. I mean, in practice, you probably would want to mask them, but it will give you it won't give you exactly the same thing. So I have this array, right, telling me the ones I want to keep. To count the number of them, you can do sum on that array, or np.sum. So I get 612 good rows out of 1,000 rows. Okay. So that's the answer to the first part. So now to clean the input array and just leave the good rows, you can assign this to a mask variable like we did before, and then do let's say y equals x mask. So now y should be the cleaned version with just 612 rows. So if I do shape, then it tells me, yes, I have an array with 612 rows and still 5 dimensions. So this last part is working, yeah?
Just out of curiosity, do you have any idea what isnan?
Isnan?
Yeah, how it works?
Yeah, so at a low level, it actually, I'm not sure exactly what C function it would call, but it checks the like the bits and the floating point number itself. So they're in a 64-bit floating point number, there's some bit patterns that represent nans. So it will probably just be checking if it's one of those bit patterns. Oh, yeah, sorry.
Do you really need the np.all in like the N94 when you say math equals np.all characters? Like, do you really need the np.all? Like, you can just see the result perspective.
So if you just have
Well, like, keep it in parentheses. And I think I got the same result without the np.all.
so you just have this, or
No, I had like parenthetically so the np.any like parenthetically. I basically had the same thing kind of word without the result dot all and got the same result. Am I crazy?
I think you need all or any, but maybe.
Oh, I did the any.
Oh, okay, yeah. You can use one or the other.
Okay.
Yeah, they're both ways of checking if the condition over some array is true for everyone or none of the elements. So either one works. All right, so this last part, what we want to do is first compute the mean of all the elements. So not all the elements, but all the rows. So we want to get the mean being a single 5D one element array, or sorry, 5-element array. So to do that, we would use mean of y, and again specify the axis along which we want to compute. No, damn it, 0. All right. So this computes the mean of y, but only along a single axis. So you're doing the mean of each dimension. So that's the mean part. We want to subtract off that mean from the input, and then divide by the standard deviation, again along the first axis. So that should be the final answer. And here this is like a case where broadcasting is very convenient because you're doing some reduction operation and then you're subtracting that off of every element. And this is doing the implicit broadcasting right here. And actually, again, this step is going to broadcast as well because this is then the full size array, and this is again just a length 5 array. All right, any questions on that somewhat complicated and condensed exercise? All right. OK, so what else is in NumPy? I'm not going to do any more examples of NumPy, but just so you know, it also has, besides the basic like operations and like hundreds of useful array-oriented functions, it has a random module for all sorts of random number generation. You can draw numbers from a ton of different distributions. It also has some linear algebra stuff, some of which is in this linalg subpackage. And it also has some fast Fourier transform functions. All right, that wraps it up for NumPy. I'm going to talk about Scifi really briefly, but only just to like tell you what is in it, because it's a huge package, and it would take pretty long to go through any of it, really. So Scifi, if you think about that initial diagram I had, it's like further up the stack. Scifi is based on NumPy. It uses NumPy for a lot of stuff. It sort of extends NumPy with more functions. It's sort of interestingly, it actually predates NumPy by like half a decade. Scifi was created in, I think, 98 or 99, whereas NumPy is from 2006. And actually NumPy, that's because NumPy had some predecessors called Numarray and Numeric that sort of got refactored and beautified into NumPy. But originally, Scifi is just a collection of wrappers for stuff from the Fortran netlib libraries. So just to kind of give you an overview of what's in it, it has stuff for clustering. It also has FFT, integration, interpolation. There's a whole bunch of random stuff in there for I/O to specific formats. It also has linear algebra, just like NumPy. ND image is like more complicated things you want to do with multidimensional arrays. Optimization is one that I use a lot. Sparse matrices, whole bunch of special functions, and some statistical distributions that Daniela will talk about more, I think. But basically the takeaway here is that if there's something you need to do scientifically, it's not in NumPy, then like Scifi is kind of the first place to look to see if it has what you need. Yeah, and be aware of this overlap that both NumPy and Scifi have FFTs and linear algebra stuff. I think my understanding of the reason for this is that NumPy is sort of like under the covers, NumPy is only C, whereas Scifi is Fortran. So I think whenever there's an overlap, the Scifi ones are preferred if you have an option, but usually it doesn't matter too much. Now, for astronomy-specific stuff, I just kind of want to briefly show you what's in the Astro Pi package. So Astro Pi is this Python package that's probably a lot of people are aware of. It started in 2011, and this was sort of in response to increasing duplication in Python and astronomy as it was becoming more popular in Python. There were all these packages springing up. And finally, someone on the mailing list was like, all right, do we really need 5 different packages to translate between coordinates? We should really like get together and all agree on a single, at least base package for doing all the common stuff we all have to do. So initially, it brought together some existing Python packages. So for fits files, originally, AstroPi.io fits used to be PyFits, kind of got merged in. There was a package for dealing with ASCII format tables called ASCII table that's now in AstroPi.io.ASCII. For world coordinate systems, mapping from image arrays to coordinates on the sky, there was a package called PyWCS that's now merged in. And the AstroPi.cosmology package for doing like cosmological distance calculations used to be this package called Cosmolopi, but it's actually had a lot of improvements to it after it got merged in. Since then, it's expanded quite a bit. There's now a table class that's pretty fully featured. That's kind of similar to a pandas table for people who are familiar with that. But it has some different features. There's a units package and quantity arrays. So this is like when you can basically attach units to an array and then pass around those units, and we'll do all the unit operations for you. There is a coordinates package for dealing with translating between different coordinate systems. Time for dealing with all sorts of times that we have to deal with, like MJDs. There's a small stats package that has additional usually astronomy-specific statistics stuff that's not in SciPy stats. There is a modeling package, but I don't really know much about it. So, and there's some stuff for virtual observatory format files, and a few astro-specific analytic functions. And there's a number of smaller utilities, but this is sort of like the main contents I think I've covered. So.
How many people in this room have contributed to Astro Pi? Put up your hand if you contributed. So keep your hand up for a second. So you can look at the few developers here.
I contribute documentation, not code.
Yes, and Astro Pi. That counts. Yeah, and Astro Pi has pretty good documentation. There's a lot of it.
One of the things that could happen this week is there are places where people could look at Astro Pi. There's a lot of simple places.
You have some sort of coverage, like, do you know where is missing that's important already? That you can look to?
Not off the top of my head, because my head is so full of things. If I thought about it, I could. Where I contribute documentation is when I am working with something, I'm learning something like, this was super confusing. Like, maybe I learned how to do it. Like, let me rewrite this.
I think the answer is Travis Fields. There's been discussion about that. Travis Fields can be configured to explain what this document is. They are not.
No, I'm not talking about this in Doctrine. I'm talking about really, like, in order for me to understand the unit package, it would have really helped me to have had this sentence at the beginning.
Sure.
That's,
But there's both of those.
yeah.
Isn't there a list of requested tutorials like that too?
Yeah, there's a list of requested tutorials. Tutorials, though, are a bigger ask, right? Rather than just as you're learning, if you're using an Astro Pi package for the first time, and then you read the documentation for it, and as you're going through it, you're like, oh, it would have been helpful for me if there would have been a link to this here instead of me having to Google it and spend 20 minutes on Stack Overflow trying to figure it out. Now that I figured it out, let me add this to the documentation. So I've done it that way.
Yeah, so besides the documentation itself, there's a separate section of the Astro Pi website that has sort of extended tutorials that put together a lot of different things that, the documentation is specifically if I want to use this module, how do I do it, and what's the call signature. These tutorials are more like, I want to do this analysis, how do I accomplish it with Astro Pi? So it's using a whole bunch of things at once. So yeah, so there's like a handful of these now. So yeah, if you have anything that you see missing, or if you feel up to adding a tutorial, I'm sure it's always greatly appreciate new developers on Astro Pi. So I have like 2 minutes left. So, all right, I'm going to go through this example really quick just to give you a feel for like coordinates, for example, from Astro Pi. So this is how you would. So say you have a list of R index, as often happens, and I've just sort of randomly scattered them throughout the sky here. And say they're in degrees, right? And you want to convert them, and say they're in the FK5 or ICRS system, but you want to convert them to galactic because you need to have galactic coordinates for some reason, right? So how you would do this is you would create this coordinates object that holds all your RA decks, and you have to tell it on input what the units are. So I'm saying that both the units for RA and deck are both degrees. So if I do this, I will get a sky coord object that contains all these, how many did I say, 100 coordinates. And to convert to galactic, you simply call this .galactic attribute. And now you have them in galactic. But how do you actually, if you want to know the specific values at each point, how do you actually get those out? You would access the longitude or latitude attributes of that. So .l will give you the longitude, yes. And it even formats it nicely into, yeah. I kind of agree. It formats it horribly.
But I assume you can tell it's formatted how you like.
Well, so still isn't super useful because, like, what if you actually want a value, right? So you're like, okay, what is this thing? I had to call type on this to figure out what it is. It's a longitude object. If you actually want an underlying NumPy array that gives you the straight up values, you have to say, okay, give me the longitude in degrees, and now I've got an array that I can then, if you had to have just straight values in degrees, this is how you would do it. So that's just a quick example. A lot of stuff in AstroPi has sort of like units added to it, which can be either good or bad depending on who you ask. But it does make you be explicit about, I want this in degrees. All right, so yeah?
Small question. A couple of months ago, maybe you know this off the top of your head. A couple of months ago, I was trying to deal with a matrix that has different units for every column.
I don't know of any way to do that. I mean, using I don't think the quantity object in AstroPi can handle that because all the quantities are like unit and then a block array. There's no like multiple units. So you could do you'd have to do separate. Yeah, you pretty much if you need to have a matrix that you are passing to some linear algebra routine, you pretty much got to translate it into a plain NumPy array, I think. Okay, so last thing. So that's AstroPi. That's kind of like the base library that a lot of people use in Python. If you need to do more specific stuff that's not in that package, there are things known as affiliated packages for AstroPi. So on the website, there's this affiliated packages page. And these are kind of separate packages that build on base AstroPi, but they might contain stuff that not everyone needs. So for example, SN Cosmo is one that I developed that has supernova specific stuff that most people who use AstroPi aren't going to be interested in. But it uses AstroPi and it provides specific functionality for doing like supernova cosmology analysis. So there's this whole list of things. It's actually quite long now. There's like 20 packages. In addition to that, there is also on the Python package index, you can search for, if it comes up, packages that have a description of being specific to astronomy. And if you do this, you get something like 230 packages at this point. So if there's something you need so this is like sort of the first thing I do to see if someone has already done something in astronomy in Python. And then I kind of search through this list and see what's there. Yeah?
So how do you assess which of these packages are good and can be trusted, and which ones are kind of shoddy jobs that I should, be very skeptical of?
The same way you assess everything in science.
That is not entirely a bad suggestion. Python in Astronomy Facebook, which is basically questions like that. I need to fit a dozen spectra using stellar population templates. What do you suggest?
Who here in this room is not a member of the Facebook astronomy?
Well, Python
No,
astronomy.
Oh, Python and astronomy. Python and astronomy.
Specifically known for Python. So, yeah, sign up for that. There's a bunch of people, and people ask questions exactly like that. I have tried the following two packages, none of them work. And sometimes the developer of one of those packages will say, oh, I'm sorry.
There's also a website, astronomers.io, that is sort of a alternative to the Facebook astronomers group that is also designed to have some, discussion of code on it. I think it hasn't quite caught on yet, but I would like it to, personally.
The other thing that you could do is tweet and tag @AstroPi, even if it's not an AstroPi question, but the people who are following that AstroPi tag will funnel it in the right direction. Seriously.
It's a different way of doing things.
It's crowdsourcing your questions.
Yeah.
There's so many questions about Python that are in that result. It's super efficient. I mean, even
response if you're a potential employer.
I also make good responses. I'm not a potential employer.
People are too bored and they're not.
No, I was joking. I really do think that Twitter is a good environment for us to work, partly because it is truly an open platform for discussion. So I think Twitter or astronomers.io.
All right. So on that note, I think we have a coffee break, and we can all argue about Twitter while I drink coffee.
Until 11 o'clock, and then we'll go on with the tutorial. I hope there's still coffee.
Thank you, Kyle.